This is EC23 Performance Task number 10, and I am Francis Aniskaya from EC3B. Today, I will be reporting about Synchronous Digital Hierarchy, or SDH. So what is SDH? SDH stands for Synchronous Digital Hierarchy and refers to a multiplex technology used in telecommunications. SDH allows data streams with low bit rates to be combined into high-rate data streams. Since the entire network is synchronous, individual bit streams can be embedded into it and extracted for high-rate data streams relatively easily. So here is an example diagram of how SDH can work. SDH combines n signals with a bit rate of b to form data streams with bit rates of n times b on a synchronously docked network. The individual transmission paths have minimal clock discrepancies. The synchronous mode of operation allows low-order multiplex systems such as communication links for telephone systems to be inserted in hierarchy levels and then removed again via add and drop. In accordance with the levels defined by the standard, SDH recognizes different hierarchies such as STM1, which has 100 STM1, which has 155 megabits, STM4, which has 622 megabits, and STM16 with 2488 and STM64 with 9953 megabits and more. About 5% of the gross data rate is reserved for OAM tasks or operations, administration, and maintenance. The data is transparently transported over the SDH network in containers. SDH in GSM. SDH usually uses wired or wireless media such as digital microwave and optical media such as optical fiber. The wide networks of the Global System for Mobile Communications or GSM service have very good performance because of the synchronous nature of SDH technology. If synchronous transmissions were not employed, GSM calls would drop out too frequently. SDH technology allows the wired or wireless receiver to synchronize on an incoming data stream. This makes it possible to propagate a timing reference down the network. In a cluster of SDH sites, a master clock will have a very accurate timing source. One good source of global bit timing is the Global Positioning System or the GPS satellite, which are able to provide accurate timing reference for data bits. For wireless transmission, the digital microwave equipment is very popular for hops of about 5 kilometers, 25 kilometers. Typical digital microwave equipment may carry 4 or 8 E1 links, a European standard 32-channel carrier. One E1 carries 2048 kilobits per second, so an E1 link carries 32 by 64. In GSM networks, each cell may need up to 8 channels on an E1 carrier. There are 32 channels, so there will be about 4 channels allocated to each cell site. In order to share one E1, there is a need for an add or drop multiplexer or an ADM. The ADM provides the channels for time slots while also supplying the channels for the audio derived from subscribers from the site. For the above GSM network, there will be 4 cell sites being supported by one E1 carrier. The first site will manage 4 channels and leave the rest of the channels for the other sites to add signal and drop signal into. Meanwhile, all the cell sites in hierarchical structure will need to be synchronized all the way to the Mobile Switching Office or MSO. The term backhaul refers to the entire set of digital signals that need to be hauled back to the switch or MSO, where these signals are either returned to the local network of cell sites or passed into another network via a switch called gateway MSO. So here's the SDH frame structure. The frame has a repetitive structure with a period of 125 microseconds, the same as for the pulse code modulation or PCM, and consists of 9 equal-length segments at the gross transport rate of 155.52 Mbps for the base synchronous transport module or STM1. There is a burst of 9 overhead bytes at the start of each segment as shown in the figure. This figure also depicts how the SDH frame at STM1 is conventionally represented, with segments displayed as from 9 rows and 270 columns. Each byte is equal to 64 kbps. So each column of 9 bytes is equal to 576 kbps. So you can see here each column, which consists of 9 carriers, is equal to 576 kbps, with each box equal to 64 kbits. The first 9 columns, containing the section overhead or SOH for transport support features such as framing, management operation channel, and error monitoring, with the first segment containing the frame word for the multiplexer alignment. The remaining columns can be assigned in many ways to carry lower bitrate signals such as 2 Mbps. Each signal has its own overhead. Here is a diagram for the payload capacity. For transporting PDH traffic signals, payload capacity is allocated in an integral number of columns, inside of which are management overheads. Associated with the particular signal as this figure depicts, the first level of division in the administrative unit or AU, which is the unit of provision for bandwidth in the main network. Its capacity can be used to carry a high bitrate signal such as 45 Mbps or 140 Mbps with the two sizes of the administrative unit 3 and administrative unit 4 respectively. This figure shows an administrative unit 4 which occupies all of the payload capacity in an STM1. An administrative unit can be used to further divided to carry lower rate signals, with each with a tributary unit or TU, of which there are several sizes. For example, a tributary unit 12 carries a single 2 Mbps signal, and a tributary unit 2 carries a North American or Japanese 6 Mbps signal. So you can see in this diagram, we have here the path overhead for a higher order VC. This is where the administrative units go, and this is where the tributary units go. So this is an example of an STM1. And here we have the path overheads for lower order VC. Here is the tributary units containing lower order VC number 2 and the pointers. A VC is a virtual container. And an administrative unit can be a higher order virtual container and an administrative unit pointer. And That is the end of the presentation.